The two goals of congestion control are fairness, meaning every sender gets their fair share of the network resources, and efficiency, meaning that the network resources are used well. In other words, we shouldn't have a case where there's spare capacity or resources in the network and senders have data to send but are not able to send it. So we'd like the network to be used efficiently, but we'd also like it to be shared among the senders. We can represent fairness and efficiency in terms of a phase plot, where each axis represents a particular user or a particular sender's allocation. In this case, we just have two users, 1 and 2, and we represent their allocations with x1 and x2. If the capacity of the network is C, then we can represent the optimal operating line as x1 plus x2 being some constant, C. Anything to the left of this diagonal line represents underutilization of the network, and anything to the right of the line represents overload. We can also represent another line, x1 equals x2, as some notion of fair allocation. So the optimal point is where the network is neither under or overutilized, and when the allocation is fair. So being on this diagonal line represents efficiency, and being on the green diagonal line represents fairness. We can use the phase plot to understand why senders who use additive increase, multiplicative decrease converge to fairness. The senders also converge to the efficient operating point. Let's suppose that we start at the operating point shown in blue. At this point, both senders will additively increase their sending rates. Additive increase results in moving along a line that is parallel to x1 and x2, since both senders increase their rate by the same amount. Additive increase will continue until the network becomes overloaded. At this point, the senders will see a loss and perform multiplicative decrease. In multiplicative decrease, each sender decreases its rate by some constant factor of its current sending rate. For example, suppose that each one of these senders decreases its sending rate by half. The resulting operating point is shown by this second blue dot. Note that that new operating point, as a result of multiplicative decrease, is on a line between the point on the efficiency line that the senders hit and the origin. At this point, the senders will again increase their sending rate along a line that's parallel to x1 equals x2 until they hit overload again, at which point they will again retreat towards the origin. You can see that eventually the senders will reach this optimal operating point through the path that's delineated by the blue line. To think about this a bit more, you can see that every time additive increase is applied, that increases efficiency. Every time multiplicative decrease is applied, that improves fairness, because every time we apply multiplicative decrease, we get closer to this x1 equals x2 line.